This video provides a general introduction to hypothesis testing. There are two main branches of inferential statistics: estimation and hypothesis testing. Opinion polls are an example of estimation. Hypothesis testing asks whether it is reasonable to assume a specific value for a population parameter based on our sample results. Both methods attempt to generalize or infer something about populations based on sample data. Hypotheses are precise, testable statements about research results. We test at least two hypotheses simultaneously: the null hypothesis and one or more research hypotheses. Hypotheses refer to population parameters. The null hypothesis states that there's no real difference or effect, that results are due to chance variation. The research hypothesis states that results are due to a real effect or difference in the population. The research hypothesis can be either two-tailed or one-tailed. Suppose a researcher is testing the effectiveness of two different medications to treat adults with high cholesterol. The null hypothesis states that there is no difference in mean LDL cholesterol between the two medications. The statement includes both the parameter being tested and the population of interest. The research hypothesis is that there is a difference in mean LDL cholesterol between the two medications. This is a two-tailed or non-directional hypothesis because the researcher is not looking for one medication to be better than the other. This is a shorthand way to state these hypotheses, using subscripts for each group. If the researcher believed that one medication would produce better results than the other, the research hypothesis would be directional. Researchers studying the health of graduate students looked at the proportion who are physically fit. The value of 0.5 would be based on theory or previous research. The population is current graduate students, and the parameter is the proportion who are physically fit. The research hypothesis does not indicate an expected direction for the difference, so it is two-tailed. We can also write this in shorthand, using the symbol for the population proportion, p. The research hypothesis would be one-tailed if the researchers expected this proportion to be less than or greater than 0.5. Hypothesis testing uses a reasonable doubt standard. Researchers start with the assumption that the null hypothesis is true, but are usually looking to reject it. If the null hypothesis does not seem reasonable based on the evidence collected in the study, then it is rejected, and the research hypothesis is considered more reasonable. If the null hypothesis seems to be reasonable based on the evidence, then it is not rejected. We can't prove anything with statistics. The process of hypothesis testing is based on disproof, not proof. Dental amalgam and water fluoridation are hot topics in the dental world because they involve health and safety and can therefore be emotionally charged. People want proof that it's safe. But we can't prove a negative unless we have every single member of a population available to us and none of them show adverse effects. And if we had an entire population, we would not need statistics. The null and research hypotheses account for all possible study outcomes. If results provide evidence against the null hypothesis, then it simultaneously provides support for the research hypothesis. This makes researchers very happy. But if there is insufficient evidence against the null hypothesis, then it is retained, which means that the research hypothesis is not adopted, which generally makes researchers very sad. We never accept the null hypothesis. Instead, we say that we fail to reject or concede it. This is because we cannot prove a negative. Think of this on an individual level. If a diagnostic test is used to diagnose lung cancer and the result is negative, we concede that the test has failed to show evidence of cancer. This doesn't prove that the patient is cancer-free. It only means that the test did not detect cancer. Now for some deep statistical thoughts. The null hypothesis is either true or it isn't. For example, there either is or is not a difference in mean LDL cholesterol between the two medications. But we never know whether the null hypothesis is true because we don't have all the data. Instead, we make a decision about the null hypothesis based on our sample results, and samples provide only limited information that varies from sample to sample. Therefore, there is always a risk of making the wrong decision when testing hypotheses. There are two types of error associated with hypothesis testing. A type 1 error occurs when we reject a true null hypothesis. We reject the hypothesis when we should not. A type 2 error happens when we fail to reject a false null hypothesis. We don't reject it when we should. It is impossible to completely eliminate the risk of these errors, but we can manage or limit them. We contain the risk of type 1 errors by setting the significance level, alpha. You are probably familiar with this term. Alpha represents the researcher's maximum allowable risk of making a type 1 error. Generally, this value is either 0.05, 0.01, or 0.10, with 0.05 being by far the most common. A significance level of 0.05 means that the researcher limits her risk of a type 1 error to no more than 5%. This is a fairly low risk tolerance, so while statisticians must deal with uncertainty, they are for the most part risk-averse. Another term that you may be familiar with is the p-value. This is the probability of the data when the null hypothesis is true. The p-value ranges between 0 and 1 and tells us how consistent the data are with the null hypothesis. A large p-value shows consistency between the data and the null hypothesis, so we would not reject it. But a small p-value indicates inconsistency and would therefore lead us to reject it. Both the significance level and p-value are probabilities under a sampling distribution that represents the null hypothesis. This makes them conditional probabilities. They are conditional upon the null hypothesis being true. The researcher sets the significance level before collecting data, and the p-value is directly tied to study outcomes. Both terms are reported in almost every scientific article. By indicating the significance level, researchers tell the reader their tolerance for type 1 errors. Here is an example of statistical test results. The p-value tells us that the probability of getting results like these when the null hypothesis is true is only about 2%. The p-value attaches to results of all hypothesis testing and is not to be confused with p and p-hat, the parameter and statistic, respectively, for proportions. Let's look more closely at the significance level. In the example of graduate student physical fitness, the null hypothesis states that the proportion of graduate students who are physically fit is 0.5. We can use this information to draw the sampling distribution of p-hat, the distribution of all possible values for the sample proportion when the null hypothesis is true. As long as the rule of thumb is met, this distribution will be approximately normal and can be used as a model to test the null hypothesis. Any of these values for p-hat are possible when the null hypothesis is true, but researchers have to decide in advance which values they'll take as evidence against the null. Should they reject the null hypothesis if p-hat is here? What about here? Would it have to be out here before they should reject it? Setting the significance level helps researchers make this decision. This is a two-tailed test because the research hypothesis is non-directional. Let's suppose that the researchers used a significance level of 0.05. Alpha is a probability or area in the tails of the distribution. For a two-tailed test, alpha is divided evenly between the two tails. Any value for p-hat that falls in the tails beyond these points will result in rejection of the null hypothesis. The researchers still risk making a type 1 error because such values are possible when the null hypothesis is true, but they limit this risk to 5%. The null hypothesis is either true or false. If we had access to the entire population, we would know this real-world state and wouldn't need statistics. However, we must make a decision based on sample information, and samples fluctuate. If the null hypothesis is true, and we reject it, we make a type 1 error. Setting the significance level puts a limit on this risk. If we fail to reject the null hypothesis when it's true, we've made a good decision. If the null hypothesis is false, and we reject it, we have also made a good decision. The ability to reject a false null hypothesis is called the power of the test. And if we fail to reject a false null hypothesis, we make a type 2 error. We always want to be in one of these quadrants, and preferably here because we are usually looking for evidence to support our research hypothesis. Hypothesis testing involves deciding whether the data provide sufficient evidence against the null hypothesis. If results are consistent with the null hypothesis, then we do not reject it. If results are not consistent, then we reject the null and decide that the research hypothesis is a better fit. We always risk making a mistake with statistics because we don't have all the information from the population. A type 1 error occurs when we reject a true null hypothesis, and we limit this risk by setting the significance level. A type 2 error happens when we fail to reject a false null hypothesis, and we control this risk by setting the power of the test.